Welcome students to the class of Control System 1. I am Priyanjali Mukherjee, Assistant Professor of Electrical Engineering Department of Narula Institute of Technology. In this video, we will discuss on the stability of the Blode plot. In this lecture, we will also discuss the gain crossover frequency, the phase crossover frequency, the gain margin and the phase margin, the stability conditions of the Blode plot and transfer function from the Blode plot with the examples. So let's start with the gain crossover frequency and the phase crossover frequency. Now you are familiar with the Blode plot, and you know that the Blode plot has two parts. One is the magnitude plot and another one is the phase plot. In the magnitude and the phase of the frequency are plotted against the frequency directly on the linear scale. But the main disadvantage of the linear plot is the cumbersome computation. So it is convenient to plot the magnitude and the phase shift curve with the logarithmic scale. And in Blode plot, we use the logarithmic scale. Now, in the plot of the magnitude of the sinusoidal transfer function, we have plotted against the frequency in logarithmic scale, and in the phase plot, the phase angle has been plotted against the logarithmic frequency. And in magnitude, it is converted into decibel unit by multiplying it 20 log of mod of Gj omega, where the base of the logarithm will be 10. So now we need to find out what is the gain crossover frequency. Now the gain crossover is actually a point on the G of J omega plot at which the magnitude of G of J omega crosses the 0 dB. And the gain crossover frequency is the frequency of G of J omega at which the magnitude plot crosses 0 dB line. And the phase crossover means it is a point on which the phase plot, that is the angle of Gj omega plot, at which the phase plot crosses minus 180 degree. And the phase crossover frequency is the frequency at which the phase plot crosses minus 180 degree. Now we know that the reference line for the magnitude plot is 0 dB line, and for the phase plot the reference is minus 180 degree line. So if we consider this graph, the magnitude plot cuts the 0 dB reference line at this point. So this point is known as the gain crossover frequency, or denoted as GCF. And the phase plot has intersect the reference line at this point. So this point is known as the phase crossover frequency, or PCF. This is the reference line minus 180 dB. Next is the gain margin and the phase margin. So gain margin is the amount of gain that can be needed to make a closed loop system become unstable. And the gain margin is actually the difference between the reference line 0 dB and the gain at the phase crossover frequency that gives a phase of minus 180 degree. That means to evaluate the gain margin, we need to refer the phase plot and determine the frequency at which the phase is 180 degree. and that frequency is known as the phase crossover frequency. And at that frequency, we need to look at the magnitude plot and we need to draw a perpendicular till it intersects the magnitude plot. So, if we draw the perpendicular from this TCF, it cuts the magnitude plot at this point. So, the difference between this point to the 0 dB line is known as the gain margin of the system. Similarly, to find out the phase margin of the system, first we need to consider the GCF. So, GCF means the point where the magnitude plot intersects the reference line. So, this is the GCF point. Then we draw the perpendicular till it cuts the phase plot. And the point where the phase plot intersects this perpendicular line, the distance from that point to the reference, that is minus 180 degree, is known as the phase margin. So, let's take an example. So, here we have considered one open loop transfer function Gs equal to 1 by s into 1 plus 0.02s into 1 plus 0.04s. So, here we need to find out the stability of the system. So, as the system is given in the time constant form, that's why we will not consider the first step. So, first we will consider the equivalent transfer function by putting s equal to j omega in this equation. So, it becomes 1 by j omega into 1 plus 0.02 j omega into 1 plus 0.04 j omega. Next, we need to calculate the starting point. So, as we know, the omega is varying from 0.1 to infinite. So, that's why I have considered the omega equal to 0.01 over here. And the starting point depends on this factor 1 divided by j omega. And to convert it into decibel, we will multiply it with 20 log 1 by omega. Now, we put the omega equal to 0.1, which gives us the value 20 dB. So, 20 dB is the starting point of the graph. Next, we will consider the table for the magnitude plot. Here, the factors with respect to the corner frequencies and the slope of each factor and the net slope has been calculated. So, first we need to find out the corner frequency for all these terms. So, for the term 1, the corner frequency is 0. For the j omega term, there is no corner frequency, that is again it is 0. And for this 1 by 1 plus 0.02 j omega, the corner frequency becomes 1 divided by this t. So, it becomes 50, and for 1 by 1 plus 0.04 j omega, here t is 0.04, that's why the corner frequency is 1 by 0.04, which becomes 25. So, next we need to arrange all these corner frequencies into the increasing order. So, the corner frequencies has been put in the increasing order in this table. And we will write the factor corresponding to each corner frequencies in this table. And next, we will find out the slope contributed by each of the factors. Now, we know for the factor 1, the slope is 0. For the 1 by j omega, it is located at denominator. That means the slope will be minus 20 dB per decade. And all these terms are located at denominator. So, for each term, the slope will be minus 20 dB per decade. Next, we will find out the net slope. Net slope is nothing but the summation of the previous slope and the current slope. So, for the first line, the net slope is 0 because slope contributed by the factor 1 becomes 0. Next, we will add this 0 with the next slope minus 20 and we will get the net slope minus 20. And for the next line, this minus 20 will be added with this minus 20 and it will give us minus 40 and so on. So, final net slope becomes 0, minus 20, minus 40 and minus 60 dB per decade. So, this table has been created for the magnitude plot. Then to find out the phase plot, we will consider the phase angle, and the relation of phase angle becomes, for this j omega term, this is minus 90, For this term, it will be minus tan inverse 0.02 omega, and for this one, minus of tan inverse 0.04 omega. Now we will vary the value of omega from 0.1 to infinite, and we will find out each of the angles for the values of the omega. And the table has been completed for the phase plot. So this one is the Blode plot. The reference line for the magnitude plot is 0 dB, and the reference line for the phase plot is minus 180 dB. So the starting point is 20 dB per 20 dB, and from this 20 dB, the first slope is minus 20 dB per decade, and it will be a straight line with the slope minus 20 dB per decade until the next corner frequency comes. And we got the first corner frequency equal to 25 radian per second. So up to 25 radian per second, the slope is minus 20 dB per decade. And here also I have represented that each small box along the y-axis in the magnitude plot represents the 4 units. And for the phase plot, each small box along the y-axis represents 2 units. So, up to first corner frequency, that is the 25 radian per second, the slope is minus 20 dB per decade, and at this corner frequency, the slope has been changed, and the slope has been changed into minus 40 dB per decade. So, minus 40 dB per decade slope is represented by this dot line, and it will be solid up to the next corner frequency, that is 50 radian per second. So this one is the next corner frequency, that is the 50 radian per second, and then the slope has been again changed from the minus 40 dB per decade to the minus 60 dB per decade. So from the corner frequency omega equal to 50 radian per second, the slope has been changed and it is minus 60 dB per decade until it reaches the infinite. So this one is the magnitude plot of that system. Next, we will consider the phase plot, and in phase plot, the omega is varying here from 0.1 to infinite, and we will vary the values, and according to the omega, we will plot each phase angle, and then we will get this phase plot. So, from this magnitude plot, we can find out that the magnitude plot cuts the 0 dB line or the reference line at 1 radian per second. So this one is the 1 radian per second because this line is 0.1. That means after 1 decade it will be 1. So this one is the 1 radian per second and gain crossover frequency is 1 radian per second. Next we need to find out the phase crossover frequency, and from this graph we can say that phase crossover frequency has occurred at this point, and this point is the total 35.35 radian per second. From this graph, we can find out this GCF and PCF. Next, we need to find out the gain margin and the phase margin. So, to find out the gain margin, we will draw the perpendicular from the PCF. So, this one is the PCF, and from the PCF, we have drawn the perpendicular and until it intersects the magnitude plot. So the magnitude plot cuts the perpendicular line at this point. So we will draw this horizontal line parallel to horizontal line, and the distance from this line to 0 dB line, which is actually 34 dB, is the gain margin. And the distance between this point to this 0 dB line is 34 dB. So the gain margin is 34 dB. That means here the gain margin is positive. To find out the phase margin, we will consider the GCF point. And from the GCF, I have drawn the perpendicular line and it cuts the point at this point. And we will find out the distance from this degree to minus 180 degree. So that will be the phase margin, and it becomes 86.6 degree. So we can say that both the gain margin and the phase margin are positive, and hence we can say the system is stable. So in this way, we can find out the GCF and PCF, and from the GCF and PCF, we can find out the gain margin and phase margin, and finally comment on the stability. So let's check some stability condition for the Blode plot. So if the phase margin and gain margin both are stable, both are positive, then the system will be stable. And if the phase margin is negative, then the system will be unstable. And generally for the first and second order system, the gain margin is infinite, so it becomes stable, and negative gain margin generally becomes unstable system. And for the minimum phase system, both the gain margin and phase margin is stable, then closed loop stable system may be unstable, either the phase margin or gain margin is negative. So here we can see that here if the phase plot is over the minus 180 degree line, then phase margin is over positive, and here the phase margin is negative because it is cut the minus in the lower half region of 180 degree line. And here also if it intersects the plot above the reference line, then means it has the negative gain margin, and if it intersects below the 0 degree line, then it gives the positive gain margin. So if gain margin and phase margin both are positive, then the system will be stable. So here we will discuss on how to find out the transfer function from the Blode plot. So if the experimental data is with us and we can plot the Blode plot from that experimental data, then we can easily find out the transfer function from the Blode plot. And a sinusoidal input at a given frequency is applied to a linear time invariant systems, and the steady state output is measured, which is actually sinusoidal with the same frequency as the input but different in magnitude and phase. And the ratio of the amplitude of the output to the amplitude of the input is equal to the magnitude for that particular frequency. The phase difference between the input and output gives the phase response for that frequency, and this process can be repeated over the required frequency range. So when the experimental values are available, then Blode plot can be obtained by plotting mod of Gj omega in dV versus log omega, and that plot is called experimental Blode plot. And to find out the transfer function from the Blode plot, we need to find out the asymptotes, that the straight lines. And after getting the straight line approximation, we can use the properties to find out the Blode plot to arrive a possible transfer function to fit the Blode plot. So here are the steps. So first step, we will find out the system type from the slope at the low frequency ranges, that means for the leftmost part. So if the low frequency slope in dB per decade is 0, then the type will be 0. And the gain, the transfer function at the gain will be A equal to 20 log K. Because if the low frequency asymptote is a horizontal line through a dB, then the transfer function represents a type 0 system with the gain K and A equal to 20 log K. And if the low frequency asymptote has a slope minus 20 dB per decade, then it represents a type 1 system, and then the transfer function has a factor in form of K divided by S. For the low frequency asymptote has a slope of minus 40 dB per decade, then the transfer function has a factor in form of K divided by S square. And next step, we require that a change in slope at frequency which indicates the presence of the another factor. And if the change slope is minus 20 dB per decade, it indicates the presence of a first order factor in the denominator. So it becomes 1 by 1 plus st1. And if the slope is plus 20 dB per decade, then the transfer function has a first order factor in the numerator, that is 1 plus st2, where t2 is actually 1 by omega c2, that is the corner frequency. Omega is here corner frequency. Next, if the change in slope is minus 40 dB per decade, then a doubt will arise whether the factor in the denominator is a second order factor or the factor is a multiple pole of the form 1 plus ts whole square. So, to solve this doubt, if the error between the asymptotic curve and the actual curve is about minus 6 dB, then the factor is in the form of 1 plus st whole square that will be present in the denominator, and if the error is positive, then it will be a quadratic factor in form of 1 plus 2 zeta ts plus s square t square. That will be also present in the denominator. And in the next step, the value of gain can be calculated. So, if the value of the gain need to calculate it, we will consider the type of the system, and if the type of the system is 0, then the gain value will be k equal to 10 to the power a by 20. And for type 1 system, the low frequency asymptote has a slope of minus 20 dB per decade, then the magnitude a will be 20 log k. From that we can write k is equal to 10 to the power a divided by 20 into omega. And for type 2 system, if the low frequency asymptote has minus 40 dB per decade, then the k is actually equal to the square of the frequency at the point of intersection of the slope with 0 dB line. So, from that we can find out k is equal to 10 to the power a divided by 20 into omega square. And if the slope of the low frequency asymptote is positive, then the factors are numerator factors. And the transfer function for individual factors are assembled to get the overall transfer function. So, let's take an example. So, here a Blode plot is given and we need to find out the transfer function for the given Blode plot. So, the given plot is actually an asymptotic plot. So, therefore, no need to draw the tangents or the extra lines. So, in the low frequency range, there is an asymptote with the slope minus 20 dB per decade. So, it indicates the system type is 1 and the presence of the factor in the form of k divided by s. Now, at omega is equal to omega 1, the slope changes at minus 40 dB per decade. That means a decrease of minus 20 dB per decade. So, there exists a factor 1 by 1 plus st1, or that is in the denominator, where t1 becomes 1 by omega 1, and at omega is equal to 4, the magnitude becomes 0. So, the line joining the magnitudes omega is equal to omega 1 and omega is equal to 4 has the slope of minus 40 dB per decade. So, the change in magnitude is, this is 36 and this one is 0. So, change in magnitude is minus 36 dB. So, we can say that 40 log 4 minus 40 log omega is equal to 36. Or we can find out the value of omega from this relation and omega becomes 0.5. So, when omega is 0.5, so it is the corner frequency, then t can be calculated as 2. So, we can find out the t, and for the factor that contributes the negative slope minus 20 dB per decade at omega is equal to omega 1, the slope is minus 20 dB per decade, that is 1 by 1 plus 2s, because t has been calculated as 2. So, next, at omega is equal to omega 1, that is equal to 0.5, the magnitude is 36 dB. This is the magnitude. So, when it is 36 dB, so we can say that 20 into log k divided by omega 1, that is equal to 36, and we will put the value of omega over here at 0.5 and we will get the value of k, that is 31.55. and at the next point omega 2, that is equal to 8. So after that the slope has been changed into minus 20 dB per decade from minus 40 dB per decade. So it indicates the presence of the first order factor is the numerator, because slope has been positive, because this one is minus 40 and then due to that factor slope has been increased up to minus 20 dB per decade. That means there is a numerator factor, and that can be represented as 1 plus 0.125s, because 8 is given over here and 1 by 8 becomes 0.125. And at omega is equal to 3, the magnitude is minus 21 dB. Now at omega is equal to 4, the magnitude is 0 dB, and omega is equal to 2, the magnitude is minus 12 dB, because we know minus 20 dB per decade represents 6 dB per octave. So this slope is minus 20 dB per decade, and in octave you can change minus 12 dB. So if it is minus 12 dB, so this distance becomes, this one is minus 21 and this one is minus 12, so it is actually 9 dB. So using the formula for this section, we can say that minus 20 log omega 3 plus 20 log of this omega 2, that is equal to minus 9. And by solving, we can find out the omega 3 is equal to 22.54. And T3 is 1 by omega 3, that becomes 0.04435. So the factor becomes 1 by 1 plus 0.4435 is. Now we have find out all the three parts, and we will combine all these three parts, and it becomes 31.60 divided by S into 1 plus 0.12S into divided by 1 plus 0.04S into 1 plus 2S. So in this way we can find out the transfer function by combining each transfer function for each section of the Blode plot. These are the references. Thank you.